Module 2, Vector Calculus, Differential Equations, and Advanced Topics. Lecture 1, Scalars and Vectors. In physics and engineering, quantities are classified as scalars and vectors. Scalars have only magnitude. Examples include temperature, mass, and energy. Vectors have both magnitude and direction. Common examples include velocity, force, and displacement. We represent vectors as directed line segments and can perform operations such as vector addition and subtraction, scalar multiplication, dot product, which produces a scalar, cross product, which results in another vector. Understanding vectors and how they interact lays the groundwork for vector calculus and the analysis of multidimensional systems. Lecture 2, Vector Calculus. Vector calculus extends calculus to functions with vector inputs and outputs. We examine fields where every point in space has a vector or scalar associated with it. Three primary operations are used in vector calculus. Gradient measures the rate and direction of change in a scalar field. It points in the direction of greatest increase of the function. Divergence applies to vector fields and measures how much the field spreads out from a point. Its key in fluid dynamics and electromagnetism. Curl describes the rotation of a vector field around a point. It tells us how much and in what direction a field curls. Applications of these operations arise in electromagnetism, weather modeling, and fluid flow simulations. Lecture 3, Coordinate Systems. Working in three-dimensional space often requires adapting our methods to the geometry of the problem. Three commonly used coordinate systems are Cartesian coordinates, based on perpendicular x, y, and z axis. Cylindrical coordinates, useful when dealing with problems involving circular symmetry. Spherical coordinates, ideal for problems with spherical symmetry, such as planetary motion. Vector calculus operations like gradient, divergence, and curl change their forms depending on the coordinate system, and choosing the right one simplifies computations. Lecture 4, Eigenvalues and Eigenvectors. Eigenvalues and eigenvectors arise from linear transformations. They describe how vectors are scaled or rotated when transformed. Given a matrix and a non-zero vector, the vector is an eigenvector if multiplying the matrix by it results in a scalar multiple of the same vector. The scalar is called an eigenvalue. These concepts are crucial in structural analysis, vibration systems, principal component analysis in data science, quantum mechanics. Eigenvalues help reduce complex systems into simpler, decoupled systems for analysis. Lecture 5, Matrices and Linear Systems. Matrices are rectangular arrays of numbers that represent linear systems. They are essential for solving equations involving multiple variables. Key concepts include matrix addition and multiplication, determinants, which reveal if a matrix is invertible, inverses, which help solve systems of equations, rank, which tells us about the solvability of systems. By converting systems of equations into matrix form, we can apply powerful numerical methods for large-scale computation. Lecture 6, Differential Equations, First Order. Differential equations describe how quantities change in relation to each other. A first-order differential equation involves the first derivative of an unknown function. Types include separable equations, where variables can be isolated on either side. Linear first-order equations, solved using integrating factors. Exact equations, which can be derived from a potential function. These equations model real-world phenomena like population growth, radioactive decay, and cooling processes. Lecture 7, Second-order differential equations. Second-order differential equations involve the second derivative of a function and often describe systems with acceleration or curvature. A standard form involves homogeneous equations with constant coefficients, characteristic equations to determine solution behavior, solutions using exponential, sine, and cosine functions. Examples include spring mass systems, Electrical circuits. Oscillatory motion. Second-order equations are also crucial in structural engineering and wave mechanics. Lecture 8. Applications of differential equations. Differential equations are tools for modeling and solving mechanical vibrations, mass spring systems oscillating under various forces. Electrical circuits are LC circuits obeying second-order dynamics. Population dynamics, logistic and exponential models. Chemical reactions, rate laws and equilibrium modeling. By applying real-world conditions and boundary values, we can predict future behavior of dynamic systems. Lecture 9. Infinite series and convergence. Series are used to represent functions as an infinite sum of terms. But not all series converge to a specific value. Common tests for convergence include the comparison test, the ratio test, the alternating series test, the integral test. Convergent series allow us to approximate functions and values that are otherwise difficult to compute. Lecture 10. Taylor series and function approximation. The Taylor series expands a function into an infinite sum of its derivatives at a single point. It enables us to represent functions like sine, cosine, and exponential with polynomials. Solve differential equations numerically. Analyze physical systems using approximations. Engineers and physicists often use a few terms of the Taylor series for precise, practical approximations in design and analysis. Lecture 11. Linear programming. Linear programming is a method for optimizing a linear objective function subject to linear constraints. Key steps include identifying decision variables, writing the objective function, establishing constraints, solving using the graphical method or the simplex algorithm. Applications include resource allocation, production scheduling, cost minimization. In operational research and management science, linear programming is a powerful decision-making tool. Lecture 12. Calculus in physical and engineering contexts. Advanced calculus isn't just abstract mathematics. It's the language of science and engineering. Examples include calculating electrical fields using vector calculus, modeling chemical concentrations with differential equations, determining fluid pressure via integration of stress over a surface, finding optimal designs using Taylor series and derivatives. This integration of theory and application ensures that calculus remains a central pillar of analytical thinking. Summary of Module 2. In this second module, we explored scalars, vectors, and operations involving them, gradient, divergence, and curl in vector calculus, coordinate system transformations, matrix algebra and eigenvalues, first and second order differential equations, infinite series and function approximations, applications of calculus in science and engineering, basics of linear programming for optimization. By combining these tools, we can model, solve, and optimize real-world problems ranging from motion and electricity to economics and ecology. Closing remarks. Congratulations! You've completed the Advanced Calculus lecture series. Throughout the 2 modules, you've gained skills in differentiation and integration, function analysis and optimization, vector and matrix operations, solving differential equations, series approximation, multivariable and vector calculus, linear programming. These concepts form the mathematical foundation for advanced engineering, physical sciences, data analytics, and beyond. Keep practicing problems, visualizing concepts, and connecting mathematics to the world around you.